Today's inverted lecture is going to cover mass spec and NMR, which we learned in Chapter 9, and IR, which we learned in Chapter 2, and how we use those to determine structure and also to figure out an unknown structure. So let's start with mass spec, MS. It stands for mass spectrometry, not spectroscopy. And it gives you the mass of the compound. The units are AMU. And basically the molecular ion is your main compound, and that will be signified as M with radical cation, because that's what forms in a mass spec. So basically, to calculate the mass, you will have this isotope abundance chart. And keep in mind that you're focusing on this first column, which is you're using the mass of the most abundant isotope. So if your formula is C6H6, to calculate the mass, it's 6 times 12, because carbon's most abundant isotope is 12, whereas hydrogen's most abundant isotope is 1. So that would be 72 plus 6. Which is 78 AMU. Okay, so you use these values here to calculate the mass. The other things that mass spec can tell you, if it's an odd number, such as 121 AMU, that tells you have an odd number of nitrogens, so 1, 3, or 5. In our cases, we're just going to have 1 nitrogen. And you should know which functional groups contain nitrogen, because that gives you an idea as to the functional group. You can also get information about what we call as the M+2 peak, and that peak weighs 2 more than the molecular ion. And that tells you if you have chlorine or bromine, because for chlorine you will have a 3-to-1 ratio of M to M+2, and for bromine you will have a 1-to-1 ratio. And these come from this chart, because if you look at the most abundant isotope of chlorine, you see it's only 75% abundant. The other abundant isotope is chlorine 37, which is 2 higher than chlorine 35. So the 75 to 24 is where the 3-to-1 ratio comes from. And the reason it's M+2 is because the isotope weighs 2 more than the actual most abundant isotope. And for bromine, it's more like 1-to-1 ratio. So this is what mass spec can tell you. IR from Chapter 2, the peaks that we see are specific bond vibrations, and they can tell you about functional groups. And so if you look at your second slide, I just brought over the IR flowchart that I had showed you in Chapter 2. And IR is key for functional groups that contain a carbonyl, 5 of which you've learned. And it can be helpful for amines, alcohols, terminal alkynes. Okay, and the flow chart will help you pick those out by following, do you have a carbonyl peak, yes or no, and following down the functional group list. Proton Nmr, which is 1H NMR, tells you about the hydrogens in the sample. And we learned 4 things. The number of unique signals shows you how many hydrogens are in different environments, and these are called heterotopic. And we also had to consider symmetry. Chemical shift told you where you were at in the spectrum. You will have this table of chemical shifts for both 1H NMR and C13. You do not have to memorize these, but you should be familiar that, for instance, benzene, if you're an H attached to benzene, you tend to be in the 7 to 8 range, for instance, in Proton Nmr. So that deals with chemical shift. To the left is downfield, to the right is upfield in both cases. You learned integration, which is the number of hydrogens at each peak, and then multiplicity, which was the fine detail in a peak, and it told you about connectivity and coupling to the neighbors. And we had talked about Pascal's triangle, the n+1 rule, and peak multiplicities such as singlet, doublet, triplet, and so on. C13 NMR told us about the carbons in a sample, And we got two pieces of data from that. The number of unique signals shows all the unique carbons, and then chemical shift arguments. Okay, there's no integration, no multiplicity for carbon NMR. We also had a special technique called depth APT, and that's a way to give us multiplicity for carbon, which we didn't have before. And in this printout, the CH and CH3 are pointing up in the air, the CH2 are pointing down, and quaternary carbons, which have no hydrogens attached, do not show at all. So you still have to have the C13 plus the depth together to see your quaternary carbons. Okay? So this is a rundown of the information we get from each, and we're going to do some practice problems where we're integrating some of that data along with reactions. And so you can see some of the scenarios which questions would be asked. Okay, so let's start with the first question. What is a possible molecular formula for a compound that has a mass of 98 AMU? So this is the mass that we would get from mass spec. And it also has a peak in the IR at 1720 centimeters inverse. Okay, so let's take those two aspects separately at first. Okay, so the IR peak at 1720 centimeters, if we use our IR flowchart, basically what we're asking ourselves is what functional group could that be? And so that is in the C double bond O range, and so our answer here should be yes. And you can see 1700 to 1730, a peak in that range tells you ketone or aldehyde. And the aldehyde would also have a separate peak at 2700 centimeters, and that's for that CH. Okay, but we don't know that. All we know is we have an IR peak at 1720, and so this tells us ketone or aldehyde. And both of those functional groups have a C double bond O. And so what that tells us is we need to incorporate an oxygen into our formula. That's what that IR is giving us, extra information. And so we're going to take our mass spec data, the 98 AMU, and so with the mass spec being 98 AMU, we want to get a formula. So the number of carbons and hydrogens and so on, and we know we need to incorporate oxygen. So we can do that using the rule of 13. And so we take 98 divided by 13. And then you take 98 minus 84, and you get 14. That's your remainder, and that's the number of H. So that tells you that your formula is C7H14. And just to do a quick check, that should equal 98. So 7 times 12 plus 14 is 84 plus 14, which is 98. So that does work out. And we had mentioned that we wanted to add oxygen to this formula. We need to add oxygen in because the IR told us we had a peak at 1720. So to do that, you have to know what CH equivalents oxygen is worth. So oxygen weighs 16, so that's a CH4 group. And so you take your formula, and doing this method, you would either add in oxygen or nitrogen. Nitrogen is CH2, oxygen is CH4. So we're subtracting out CH4. We're going to add in oxygen. So C7 minus 1 is C6, and then H10O. Okay, so this is the formula that we get. What is a possible formula for the compound that would match an IR at the peak? It would be C6H10O. The second bullet point says draw a potential structure for this compound that would show a peak in the proton NMR in the 9 to 10 range. So if we look at our chemical shift charts and we look in the 9 to 10 range, we see that we have an aldehyde. So what that's telling us is we have an aldehyde and we need to draw a potential structure that has that. Before you start drawing a structure, the first thing you should do when you have a formula is calculate IHD, which tells us the number of unsaturations. And so the IHD is 2N plus 2 minus the number of hydrogens, which is 10, divided by 2, so that's 12, 13, 14, minus 10 is 4 over 2, which is 2 unsaturations. Okay, so that means that our aldehyde is 1 unsaturation, and so the other unsaturation could be a double bond or it could be a ring. And so let's do a ring because of the data that we've been given so far. So we need 6 carbons with an aldehyde and a ring. And so one example of that would be a 5-membered ring with an aldehyde coming off of it for the 6th carbon. And just to double check, C6, 1, 2, 3, 4, 5, 6, H10, 2, 4, 6, 8, 1 here is 9, 10, O. So that matches that formula, and that would just be one example of a structure you could draw that would match that data. Okay, so you could be given problems where you're just given little pieces of data, and there are many possibilities that you could have. And so you're using what you know about each of those techniques. In the second example, we had learned in Chapter 8 that you can react an alkene with HBr or HBr and peroxides, and you get a different product under each condition. And so it says that reactions below form products that are regioisomers of each other. And so draw the main product that occurs each time. So with HBr, remember that we get a carbocation, and it goes to the more substituted position. This is called hydrohalogenation. You have to consider rearrangements if it's secondary, and it is secondary, but it cannot rearrange anywhere. And so the bromine would just add, and you would get this product, which would be 2-bromobutane. However, if we carried out HBr and peroxides, the peroxides reverses the selectivity, and the bromine goes on the less substituted carbon. And so you get this structure. And this would be 1-bromobutane. And so we can prove this using data. So would the number of unique signals in Proton Nmr allow you to distinguish between these two products? Okay. So how many unique sets of hydrogens are in this molecule? That was called heterotopic hydrogens also. And so if we look, there's no symmetry, and so each set of hydrogens is unique. And so if I say A, B, C, D, we would expect 4 peaks by Proton Nmr. If we look at the hydrogens here, we also would see 4 peaks, A, B, C, D. Okay. So the number of unique signals alone would not allow you to distinguish between these two products. And so if not, could you use integration or multiplicity or both? And so if we look at the integration of these 4 peaks, of those 4 peaks, this one would be worth 3 hydrogens. And then we would have a peak worth 1 hydrogen, and then 2 hydrogens, and 3 hydrogens. If we look at the compound on the right and look at these 4 peaks, we would have 2, 2, 2, and 3. So integration would tell us a difference, because in this case we would have a peak just by itself worth 1H, and we would have no situation like that here. So integration would work. And multiplicity, would that be able to tell you the difference? Yes, and when I focus on multiplicity and just telling structures apart, let's focus on one thing that separates these two compounds, rather than assigning multiplicity for both structures, which would take too much time. And so if you're going to focus on one peak, you want to focus on the most downfield hydrogen, because that's the one that's going to stand out, and downfield was to the left. And in this case, it would be HB, because it's connected to the bromine. And again, if you're connected to halogen, you're in the 3 to 4 range. Every other peak would be in the 1 to 2 range. Okay, so I would be looking for what does the peak in 3 to 4 look like. And so HB, what would be the multiplicity? You count the neighbors, so it has 3 A neighbors and 2 C, so that's 5. And so with the n plus 1 rule, you have 5 neighbors plus 1 is 6, which is a sextet. That means HB would be 6 lines for a sextet. If we look over here, the most downfield hydrogen would be HA because it's connected to bromine. And so what would HA look like in terms of multiplicity? It has HB only as its neighbor. And so with the n plus 1 rule, it has 2 neighbor HBs, 2 plus 1 is 3, and is a triplet. Okay. So you could look at the NMR in the 3 to 4 ppm range, and you're either going to see a sextet if this product's favored, or a triplet if this regioisomer is favored. Okay. Number 3, would APT NMR allow you to distinguish between these two products? And the answer here again is yes, because APT NMR allows you to do CH and CH3 pointing up, CH2 down. If we look here, we only have 1 CH2. So we'd only have 1 peak pointing down. If we look at this compound, we would have 3 CH2s pointing down because A, B, and C are all CH2. Would mass spec allow you to tell the difference? I'm just going to take that question out. So there's an example of using structure elucidation if we're given some hints and we're trying to determine a structure, and if we have reactions already. And so I guess kind of the first problem and this last problem, you don't know what the structure is and you're trying to come up with the structure. And so here's kind of like some things to think about when you're determining a structure. If you have a molecular formula like C6H6, the first thing you can do is determine IHD. If you do not have a molecular formula, then look at the mass spectrum. Because remember, this gives us the mass. It also tells us if we have nitrogen, if our mass is odd, and if we have chlorine or bromine. Use IR to get information about functional groups, and then look at your NMR spectra. Count the number of hydrogens, count the number of carbons. Are there any elements of symmetry? Does anything stand out? Like for instance, in the first problem, a peak in the 9 to 10 range in Proton Nmr told us that we had an aldehyde. If we were looking at carbon NMR, that same peak would be in the 200 to 220 region. So things that stand out. And basically you're going to use knowledge from that together and come up with your own formula using all this. So from mass spec, you get a mass. If you have halogen, you subtract out that halogen. If you have nitrogen or oxygen, you add these in using CH equivalents, like we did on the first problem. Nitrogen is worth a CH2, oxygen is worth CH4, and then other hints from the IR can tell you whether you're going to have nitrogen or oxygen. Do the rule of 13, which we tried already. If you have any information from an organic reaction, use that as well. For instance, if I said we have a hydrobromination, then you would know that the H and bromine will add. And then lastly, you're kind of treating it like a puzzle. And so whatever puzzle pieces you can put together, you do. And just jot down any pieces you have. Okay, so let's do an example of a problem, and you will have a problem like this on your final exam where you have to put some pieces of data together. Okay, so we're told that the mass is 78 AMU and that we have an M to M plus 2 peak ratio of 3 to 1. Okay, so the fact that it's pointing out the M to M plus 2 ratio of 3 to 1 tells us that we have chlorine. And chlorine weighs 35. Okay. And then we have some Proton Nmr data with 3 main peaks. Okay, so I'm going to note that. We have 3 unique peaks by 1H. So we have 3 sets of hydrogens. And these numbers are our integration, so 2, 2, and 3. So we have 7 hydrogens in our molecule. And so when we determine a formula, it should equal to 7. And that's all I can really tell at this point. So now that I have a mass and I have a chlorine, I'm going to subtract the chlorine from the mass. So 78 minus 35 is 43. Okay, so I have 43 left over, and that is what I'm going to do the rule of 13 on. So I'm going to divide it by 13, which is 3. It has to be a whole number, and that's the number of carbons. Okay. And then you take 3 times 12, which is 36. So of that 43, 36 is due to carbon. And what's left over is 7, and that's due to H. Okay. So my formula is C3H7, and then I have to add my chlorine in. If I just do a quick check, 3 times 12 is 36, plus 7 is 43, plus 35 gives me 78. So that does work back out to be 78. Okay. And so that is my formula, and the 7 matches the 7 here. So I don't have any other atoms, because if I add the oxygen, I have to take away H's, and I see that I have all my H's here already. So that must be my formula. Once I have a formula, I'm going to calculate IHD. So 2 times n is 3, plus 2, minus 7, and then halogen we subtract, so minus 1 for halogen. So that's 6, 7, 8, minus 8 over 2, which is 0. So I have no double bonds. Okay, no rings. So I have 3 carbons, a halogen, no double bonds or rings. And so I have 3 carbons and a halogen, or my halogen could be connected on the inside. Okay. If your formula is small, you have a small number of carbons, just draw your possibilities. Otherwise, you can look at the Proton Nmr to give us hints, because the splitting, which you might not be able to see on the video so well, the splitting tells you about the neighbors, and we can use that to rule out which option is which. Okay? So we have 3 peaks, and just looking at this, the compound I drew on the right would only be expected to have 2 unique peaks, okay, because of the symmetry here. And so I can rule out that compound, and so my answer would be this. Just to confirm, let's make sure it matches the splitting. Okay. I have 3 hydrogens, and the ones connected to the chlorine are going to be the most downfield, between 3 and 4. So this would be hydrogen C. Okay. And the signal here is a triplet, which makes sense because it has 2 neighbors. B should be the most complex pattern because it's sandwiched between A and C. And so B's pattern, B has 3 A neighbors and 2 C neighbors. So that's n plus 1 is 5 plus 1 is 6, which is a sextet. So we would expect B to have 6 lines, and you can see here 1, 2, 3, 4, 5, 6. And those ratio of the lines is due to Pascal's triangle. And so the last peak is A, which is the furthest upfield, and it has 2 neighbor B protons. And so if you do the n plus 1 rule, it's 2 plus 1 is 3, which is a triplet. Okay, so A is a triplet, C is a triplet, B is a sextet. Okay, so that's putting in all of the data together to solve an unknown. If you look on Blackboard, you will see that you have 2 unknown problems to try where you have to put some data together.